Good afternoon, and thank you all for coming today to our March CADRE Symposium. Before I introduce our speaker, I wanted to introduce a couple of things about CADRE. CADRE is an informal community of folks here at OSU that are interested in promoting digital education and research. CADRE actually stands for the Coalition for Advancing Digital Research and Education. And the mission is on the slide here. We encourage anybody with an interest in encouraging projects, guiding policy, creating educational elements, anything, to join us. And there's a web page, which you see the URL there at the bottom, and you can get details there. Our next project is a student data award. So as a means of encouraging students to engage in data science and showcase their work, we have collaborated with some corporate partners to offer cash awards for folks who do outstanding work. And details are available at the URL there. And actually, I think I have a copy of our flyer here, which we'll distribute via email, and you can find in various places. The cash awards are listed down there, as well as the sponsors at the top. And for the QR codes, will take you to complete award descriptions, as well as the scoring rubrics, so you know exactly how these awards will be evaluated. And then so those awards are being sponsored by Dell and Intel. And then we also have an award that is being sponsored by Interworks. And Interworks is focusing on excellent data visualization. So students can submit works that were done as part of class projects. They can submit works that were done as part of research projects, or even things that they play with on their own time. The submission's wide open. It is limited to OSU students, though. So I encourage faculty to please share that with your students and encourage them to participate. And with that, I will lead into our speaker. Let's resume slideshow. Okay. There we go. Okay, our speaker today is Gary Grider, and Gary is the head of the High Performance Computing Group at Los Alamos National Laboratories. He has an OSU connection. He is an alum. He graduated with a degree in electrical engineering in 1981 and an MBA in 1984 before going on to his career at Los Alamos, and has been in his current position for 12 years, prior to which, as I think he just said, he was doing real work. So with that, I will turn it over to Gary, and let's hear his talk. And let's see why I'm still seeing that. Okay, I think I've got you set up there.
Oh, thanks. So, thanks for having me. I was looking around for people that do, that provide data for research in the open community, because we're not much of an open community. We're mostly classified at Los Alamos, and I stumbled on this organization, and we do some open research at LANL, and we were looking for best practices on providing that data to the open community in many ways. How do you pay for it? How do you do it right? How do you curate it so that it isn't a mess, and all those sorts of things? And so I'm hoping to learn some things from you guys. Thanks for the introduction. I've been at Los Alamos since '89. I was at Sandia before that, from '84 to '89. So I've been inside the DOE weapons complex for long time. And mostly in the computing area, and mostly in the data storage part of the computing area, but until I got 250 people working for me, and then I changed my job a lot. Los Alamos has been in computing for a really long time. We had our own computer that we built called Maniac. The mentor that when I got to the laboratory, her name is Marge Devaney, smartest woman I ever met, and she was a programmer for ENIAC. And the way you programmed ENIAC was you programmed it with wires. So she had a box of wires that she flew to Pennsylvania to run one of the first problems on ENIAC. And that was my mentor when I got to the lab, and I just thought that was really cool. It's going forward for me. Anyway, had a lot of machines. I don't know if you realize that Los Alamos was involved in the Stretch project. The Stretch project was really important for IBM. It became what was known as the IBM 360 line, but this was done before it was called that. It was considered to be a failure at Los Alamos and within IBM because its goal was to be 10x faster than the machines that came before it, and it only made 4x. And so they thought this was a miserable failure, but it ended up being essentially what IBM became. So there's beauty in failure, I guess. Went through an era with EDC machines and the Cray 1. I showed up when we had Cray X's and Cray Y's and still a few Cray 1s in the early 80s. We were one of the first people to have a thinking machine CM2 and CM5. And those machines are pretty interesting. 1-bit wide processors, 64,000 of them. Imagine programming that. You can have a variable length word. You didn't have to have a word of 64 bits. Which is pretty interesting. We've had big machines from SGI and HP and others. Roadrunner, you probably remember, was the first machine to a petaflop. It used the IBM Toshiba cell chip as its accelerator. Most recently, we've got the Cray Intel system of Trinity on the floor. I'll show you that in a minute. We had a brief encounter with a quantum annealer from D-Wave for 3 or 4 years, and then we deinstalled it. But we got some experience using quantum annealing technologies, IPS. And we're in the process of installing 2 new machines, Crossroads and NGP1. And I'll tell you a little bit about those. So first I want to talk a little bit about a project that I started in 2012. When a bunch of people were leaving the lab because the lab offered them money to leave for retirement. And it's essentially our history project. And we scanned about 50,000 artifacts, which ended up being it's many hundreds of thousands of pages. And OCR'd them and turned them into as much text and as much useful information as we could get. And one of the interesting documents that we found was this document, which was the letter from Los Alamos Scientific Laboratory. It was before it was a national laboratory, to Seymour Cray, saying that we would take serial number 1 of his first machine. And there's a whole bunch of documents in here just like this, arguments between LANL people and Don Knuth about things, and arguments with IBM on Stretch and things like that. Just fascinating stuff. And we're finding this history thing to be pretty interesting, and we're learning something from it. So a little bit of outline about what I want to talk about today. I was told that I probably need to have some upfront information about simulation. So I'll try to do that, and then I go in a little bit on to how we buy machines, and because that might be kind of interesting to some people. And then I'll start talking about data management tools. We have a lot of data management tools because of what we do at the lab, and I wanted to introduce some of them to you because I was hoping that you would introduce some of your data providing tools to us. Our current machine is this Trinity system, 20,000 nodes. It's 2016, so it's really old. 2 petabytes of DRAM, that's big. That's the biggest machine in DOE still, bigger than anything that's been built in DOE in memory size. Has 4 petabytes of a burst buffer. It's flashed here. It had 100 petabytes of scratch file system, and some campaign store, which is like object store and so forth. That machine was purchased for a reason. There was a purpose for it. It wasn't a machine that was bought to attract people to come do science. It wasn't a machine that was bought to service 400 or 600 different applications. It wasn't a machine that was built for 1,000 users. It was built for like 10 users and 4 apps, really 1. And it was built to solve a problem that we had been trying to solve for 20 years, and we couldn't build a machine big enough to do it until now. And the Navy has been asking questions about it for 20 years, and we haven't been able to answer those questions for 20 years because we couldn't run the problem. And finally we ran it. This machine is responsible for getting that behind the stockpile and, as a known problem and understood. And that's a great thing about it, but it wasn't just the machine that had to be built, it was the infrastructure around, and that's where the data part comes in. You have to build really large data infrastructures to service these machines, and especially the way we use them. So the machine was built to run a job on half the machine for 8 months to a year, one problem to try to get an answer. But we have lots of other machines. I've got them all listed over here on the right. The ones in the red are in our red environment, which is classified, and the ones in the blue are in the open environment for us. And you can see there are various kinds and generations and the like, and they all sort of have purposes. And then there's these other 2 machines that are being built. Crossroads, as I talked about, is going to be the first 12,000 Intel Sapphire Rapids chips that come off of Intel's line. I'm getting, that should be 3 months from now, 4 months from now. And then we're getting I don't know if anybody who attended GTC yesterday, I missed it, I was on a plane, but apparently they announced that Lanel was going to be the largest consumer of their new Grace chip in 2023. So we'll be getting 2 pretty large machines. They're not huge, but they're pretty large. And again, they're purpose-built. They're built for a particular set of applications, not for general, come what may HPC. A little bit of simulation background. So some of you, most of you probably know this. You've got different kinds of link scales that you have to deal with in simulation, and our applications typically have to deal with more than these at once. So, ab initio all the way up to continuum models. And again, sometimes a single code will have lots of those in them at once. So it could be 6 orders of magnitude of link scales that you have to deal with. And meshes, our applications are typically unstructured meshes with variable resolutions. And the applications that we have are both Lagrangian and Eulerian. Lagrangian, of course, is where the mesh deforms with the, so the mesh deforms with the problem as opposed to the mesh staying the same. And we're heavy into AMR. AMR is automated mesh refinement, so that's this thing over in the bottom right-hand corner. And you can see that the cells aren't the same size. Where there's a lot of action going on, the grid is finer than it is out on the outsides, on the outskirts. And that's done for a good reason. The reason you do that is because you can't buy a machine with enough memory to run the whole problem fully resolved. So you might say, well, you've got 2 petabytes of DRAM, how big of a problem do you want to run? And the answer is 100 times bigger than 2 petabytes probably. And so you have to use these unstructured sparse representations of these, in-memory representations to be able to run these problems on machines. And it turns out that it's a good trade-off because there's not a lot going on out in those particular parts of the application or the space at that time. And so really you're just interested in where the fun stuff is going on. And the fun stuff in this particular picture is right there in the middle, but it will move in a time step. And so the application has to rebalance things every so often to keep, to manage to run itself and not run out of memory. So this is all sort of simulation background. And there are different, programming techniques, MPI, threads, data parallel, domain-specific languages, and the like. You guys probably already know all this, but MPI has dominated for a long time until multi-core and GPUs, and now it's it has threads and data parallelism, CUDA, and those sorts of things. And all these things are fair game. And you see these things across the industry. Most of our applications are MPI plus some sort of threading mechanism or data parallel mechanism. And workflows. How do you get science done on a computer? You have some setup time. You've got to set it up, mesh it up, get your problem set up done. You've got to run it for a long time over and over again. You've got to take checkpoints. Why do you need to take checkpoints? If you're running a job across 20,000 nodes for 6 months, 20,000 nodes won't stay up for 6 months. You've got to take a checkpoint of your memory state in order to be able to restart when something fails, not if something fails, because it will. How often do you have to do this on a system that big? You probably have to checkpoint every 4 hours. So you write a petabyte-sized data set or whatever out every 4 hours just to keep the application running for 6 months. You also write analysis of time steps and things like that out, and post-process and all those things, visualization. And you have tiers of storage because you can't afford to keep everything in the hot tier. The hot tier for us is flash. And I have 4 petabytes of flash, and at the time that was $12 million for the 4 petabytes of flash. That's changed, but still a lot of money. And the campaign tier is disk, and the forever tier is tape. That changes from decade to decade, right? Different new technologies come along, and you get a new hot tier, and everything moves down. But anyway, storage tiering is something that's been in our lives for 30 years or more. Let me talk a little bit about DoE Labs and their mission. So a lot of people don't know that there's sort of 2 flavors of DoE Labs. There's defense programs DoE Labs, or in a national nuclear DoE Labs. Those are Livermore, Los Alamos, and Sandia. And then there's Office of Science laboratories like Oak Ridge, Argonne, LBNL, and others, PNNL and others. And Office of Science labs their mission is sort of, do great science in the name of energy, which is a good thing to be doing for the world. But that's very much not the mission of the nuclear labs. Nuclear labs have missions that, for ours, it's manage the warhead stockpile. For Sandia, it's manage the delivery mechanisms on the warhead stockpile and so forth. And so that's a very different mission than do great science in the name of energy. And therefore, the kind of computers we buy oftentimes can be very different. And even within the nuclear laboratories, the mission is really, really different. Sandia is about delivery mechanisms, electronics around the weapon and that kind of thing. Los Alamos and Livermore are about the nuclear package itself. And so, and why do we have 2 labs that do nuclear packages? Because they were set up to compete against one another on purpose, because there was no peer review. And so one reason is Teller wanted his own lab, and the other is we needed peer review, and so we got both at the same time, and Livermore was born some years after Los Alamos, but that was what it was for. And so every design for the military, for the Air Force or the Navy over the years, they would put out a call, and the 2 labs would compete for a warhead design. There's a Sandia Livermore because there needed to be a delivery mechanism laboratory next to the Livermore lab, and there's a Sandia Albuquerque because there needed to be a delivery mechanism laboratory for Los Alamos. And so that's why Sandia is split, and that's why Livermore and Los Alamos aren't. So anyway, but even within the two physics laboratories, the two weapons laboratories that are doing physics packages, Livermore and Los Alamos, there's huge differences in what we do. Because today we're not producing new weapons. I'm not saying we're never going to do that, but today we don't do that. We basically are doing virtual testing of weapons primarily, and our approaches are different. Livermore's approach tends to be very uncertainty quantify dominated. Try to quantify the uncertainties around the simulations you do. Los Alamos tends to be more about weapons performance, brute force. How do we calculate this thing from as close to first principles as we can get? Now, we can't get to first principles, but as close as we can get. And so the machines that we buy are really, really different because of that. Livermore will tend to buy machines that match that model. 10-node runs, millions of them. So they'll buy a really big machine and they'll run lots and lots of 10-node jobs. Now, these are big nodes, but why do they do that? They're running 3D jobs of fairly low resolution, and they're varying input parameters, and they're doing statistics on the answers they get based on the parameter studies they're doing to try to narrow error bars. Los Alamos, on the other hand, does the exact opposite, which is we'll take 10,000 nodes and we'll run job across it for 2 years. And so you can imagine that the kind of machine and the infrastructure you buy for one is pretty radically different than the machine and the infrastructure you put in for the other. And so I think this is really important because everybody looks at the national labs and thinks, oh, they all just do the same thing. Boy, that is really not the case. It's probably more the case in the DOE Office of Science laboratories than it is in the weapons laboratories. Anyway, so that's depicted here by this thing that I stole from Giddy Chickapelli from NVIDIA, which is you can classify these machines, based on control flow complexity and data flow complexity. Data flow complexity is like how if you could read all your data in serial or it was tightly compacted in memory and you got it and you read it in the same order you wrote it in and all the friendly stuff you could do, that would be very, very simple data flow. And very, very complex data flow would be you're trying to pick out and read it in a different order than you wrote it in. It's very sparse. You have to do pointer chasing to get to the next part of memory you want, all those things. That would be complex data flow. And the same thing for control flow. That's how branchy is your code or how, how simple, stream-oriented is your code. And so we happen to live in the upper right-hand corner for several reasons. One, we're running at any one time between 20 and 30 physics packages in a 9 million line code that took $3 billion and 20 engineers for most of their lives to write and maintain. And so it's branchy because there's so much physics going on. It's also horribly complex from a data flow point of view because of AMR and because of trying to put a 100 times bigger problem on the machine that you're trying to run it on, and you have all these sparse representations. So before you can even do 2 floating point multiplies, you've got to go out and look in tables to figure out what words of memory you need from the various pieces of memory, pull them together and do a multiplication. And so you spend almost all your time waiting on memory because everything is long latency to go get those memories. And we do everything we can possibly do to hide the fact that we have all this scattered memory. We're trying to do this. But unfortunately, 40% of the time is not spent doing floating point. 40% of the time is doing figure out how to get the memory I need, look it up in a table and do a dereference and a bunch of other integer crap just to get the information to be able to go do your floating point operation. So why is that important? Well, why would I buy a machine that has a zillion flops if my problem is waiting on memory? All I've done is figured out how to make the world's biggest heater. And so some laboratories go for the flops for good reason, probably. Their codes probably allow you to do that. Other labs don't. Why? Because probably their problem space doesn't lend itself to that. It's important. How do we buy machines? So it goes along that same line, right? So when we buy a machine, We don't buy it. We don't write down, I want a flop, or I want a petaflop, or I want an exaflop, or I want a zetaflop. We don't do that. We have a set of mini applications that represents the physics in our real applications. We can't put our real applications out in an RFP because they're classified. So we have to represent it in an unclassified way in a set of mini apps. And then those vendors that are bidding on that machine can take those mini apps and have them for months and months and months. And they're pretty small kernels. And they can do anything to them they want as long as they're solving the same problem. Anything. They have to give us what they did back when we return the bid, so we can see what they did. So anyway, we run a baseline, no change. What would you get on their architecture? They do. And then they run this is the best we could do by modifying it any way that we wanted to on the architecture that we want to bid to get it to go fast. And we look at the difference between how many lines of code, how much did they reorganize this piece of code, these mini apps, to make it run fast on their machine, and we project that onto our 20 million lines of code in our 4 apps. And we say, how much change does that imply? And what's the win? The win is it's 4 times faster, or it's 2 times faster, or whatever. And we take that into account when we buy a machine, because using up, computational physicists' time rewriting code, that's good if you can win. It's bad if you don't win. So we're not against changing code. We just want to change code where it matters, and we want this process to tell us where it matters. So that's what we do. We have these mini apps, and we basically concentrate on how many of those mini apps can we run through the machine in its 5-year life cycle, and how much effort are we going to have to expend to get that done. And we measure the bids against one another to try to figure out what to buy. And this is an analysis for Trinity. And I don't have any computer vendor names here, but what I have here is to the first one there, the very, very small set of bars in the middle. That's a machine in 2011. The next one is Trinity, which is running those mini apps on Trinity. The tall gray thing, that's the peak flops, and the blue and the yellow, or blue and the orange, are no app change and change optimized. And so the first 2 are baselines, and then the next one is, these are all in Cielo units, so the first machine, 2011 units. So from all the rest, the other 5 of those to the right are bids for Crossroads. And you can see that some of them have incredible peak flops. Those big gray bars, that's peak flops. But they don't necessarily do the same for what they actually provide us in our applications, even if we wouldn't change the applications, right? And so you can see that there's not necessarily a correlation between the number of flops you buy and how much work you get done. In fact, there's almost no correlation. It almost looks like an inverted correlation. This is not necessarily true for every lab. It's not necessarily true for every workload, but the methodology teases out what it is you should go buy. Furthermore, it teases out what you want to buy, but you can't. What you might be able to go pay somebody to change their architecture to go do. So that on the next machine I buy, maybe I've paid somebody, NVIDIA or Intel or somebody, to do something to their architecture to make them fare better in this kind of an analysis. So what's our most pressing goal in computing at the laboratory? We run these problems. About a petabyte of DRAM takes about 500,000 cores or more, 1 million cores. It takes 6 months to a year to run them. How do humans learn getting a result every 6 months? You can't. You can't talk to your neighbor about it. You get results so infrequently, you forgot what you ran 6 months ago. It's crazy, right? That's way too long to wait for a result. You can't win that way. We have to figure out how to take these runs and run them in 6 days instead of 6 months. then that's running them fast enough that you could have a meeting once a week with your team and talk about it and actually make progress with the science. There's human factors in computational science, and this is almost the most important one. If you ask people what they want predictable, they'd like to have a result every day. They would love that. They would make huge progress in science if they could just get a result every day and keep that fresh in everybody's mind and sharp people thinking about it. And the longer that goes, the less likely is you're going to win big in science because it takes you too long to do it. Unfortunately, that's where we're at today. This is how long it takes. So our goal over the next 4 to 6 years is let's reduce that down to 6 days. Now that's a pretty big goal. A factor of 30 is big. It's not unheard of, but that's pretty big. But that's what's required. And we have to run these problems. These are the problems of the day. They're the ones we have to run to certify the weapons. They're the problems that we have to run to figure out whether a weapon needs to be refurbished or not. There's figuring out whether we need to take a weapon series offline, figuring out whether to tell the Navy to roll the subs in, which is like a $10 billion bill, just to roll the subs in and pull the weapons off. It's big business. And so this is important stuff. It's monetarily very heavyweight from a government point of view. So it's important that we get this right, and it's important we do it better and better. And right now, we're not doing it too good. If it takes 6 months to get an answer, and that's just the computing part of the problem. This problem probably was started by somebody in Amarillo, Texas, taking a weapon apart. There's a plant there called Pantex. Their job is to dismantle, not just our weapons, but Russian weapons and a bunch of others. And they look at it and they say, well, this thing has pits all over the back of it. Did you know that? Give us some pictures of that. Measure those pits for us. Tell us what's going on. And we've got to figure out what that means for the stockpile. Is that, are they all duds? Will they go off? Will the safety work on them? They're supposed to be 1 point safety protected so that if the chain breaks while you're offloading it, it doesn't go off, right? You don't want that. But maybe that defect that's appeared because the weapon is 40 years old is going to make the safety not work quite right. We've got to know all that. And so what these problems are findings that we have to go chase down and figure out what to do about. And we like to close those in about a matter of 2 years because that's a long time to worry. And if 6 months of it is running one cycle of this thing, it takes way longer than 2 years to do it. And as I said, this one was a 20-year incoming problem. It's been sitting there waiting for a computer big enough to run it for 20 years. So you think computers are getting big, but the science problems are they dwarf the computers, and they will for as long as our lifetimes, I'm sure. So how do we get 30x? How do you fix that? There's sort of two ways. You can't just go brute force buy that. That would be crazy to buy a computer that big. You'd never get it to run. You'd never get your problem to scale across it. It just doesn't make any sense. You've got to figure out how to get there in some systematic way. And to do that and make it affordable, you've got to figure out, are there things in industry you can go leverage? And right now, there's sort of two things to go leverage. One of them is the GPU industry, the AI industry, the ML industry. There's this huge craze. Go do AI, go do ML. And that's all great stuff. It's great science. It's cool tools. It's going to change the world. It already has. So why not leverage that? So there's a whole bunch of computing sites that are leveraging that hot trend in applications and buying GPUs, and they're great. They got super fast memory. If you got a dense problem, they chew through it way faster than anything else. It's totally cool stuff. If you've ever seen a GPU, it is this amazing device. But it may not work for your problem. If your problem isn't dense and it's all this sparse crap, and you're spending half your time doing address dereferencing, a GPU is going to cost you more than it saves you. So there's another approach that you could take. And the other approach is, let's do what the cell phone people do, because cell phones are a pretty big deal, right? And so what did they do? Well, they said, we're going to tailor this processor to do exactly what our job is. We're going to pay to have part of the processor go do something special for me. I'm going to put an RF circuit in there because I want that. And I'm going to put, there's something like 71 or something like that, modifications to an ARM chip before it ever goes into an Apple system. And it's tailored to do what a phone does. Why not? And you can do that now. You can buy an ARM license for $10 million and you can say, go out, change this, this, and this, send it to a fab and have it done. Now it's harder than that, but it's possible. But that's another huge industry trend that you can leverage. And that looks like it's the best thing for Llano. And why? Because the GPU thing isn't working out for us. Why? Because we're doing this crazy trying to run 100 times too big of a problem on a machine. And we have to. And it looks like there are things we could easily do to, processor technology that would help us a lot. And you might ask, what would that be? Well, one of the things that GPUs have that's really cool is high bandwidth memory. High bandwidth memory today is 1.5 terabytes a second or something like that. You know how fast your memory is on your CPU? It's like 200 gigabytes a second, and that's if you've got a late model AMD, right? Sure, next generation they're going to be 400 gigabytes a second, but there's still a lot of difference there, a factor of 4 or 5. But if you can't use a GPU because you've got this crazy, ugly, sparse structure, what do? Maybe you pay somebody to put high bandwidth memory on a CPU. Why not? It's possible now. You could do it with a matter of tens of millions of dollars. And that would get us maybe a 3x. It's not 30x, but we're already 10% there, right? There's other things you could do that are similar, right? And so basically the message is there's kind of two paths. There's leverage popular apps or leverage other popular industry trends like tailoring. And we're choosing the right one, and Livermore choose the left one. And that's exactly what we should do, right? We should be diverse in what we're doing, and they should pick what's best for the way they approach the problem, and we should pick what's best for the way we approach the problem, and that's what we've done. So I promised to talk about data, and so I'll talk about data. Just some stuff that you may recognize or not, but it's interesting. The HPC community, DOE for the most part, but not totally, is responsible for a lot of solutions that are out there in the industry today. Burst buffers, the Cray data warp thing, all that stuff came on, and the related products all came directly out of HPC needs and or HPC non-recovering engineering costs or money we've paid industry to go do stuff for us. But probably more important than that is luster. Probably, if you don't know luster, if you use an HPC system and it doesn't have luster, I'd be surprised. And I can tell you where luster came from. Lee Ward and I from Sandia got in a room with DOE headquarters and said, we're going to have a parallel file system in 1999. I have a bag here. No, I don't. That's my 91 supercommittee bag. I have a bag from 1999 of a conference that we held in Santa Fe. And we invited everybody that could spell file system. Garth Gibson and all the luminaries, right? Dave Patterson came. I begged him and he came, right? And we said, we need this intergalactic file system thing. It needs to have 1,000 writers to a single file. And everybody went, you're crazy, you're stupid, stop it. And we said, no, that's what we need. And Peter Brahm and Garth Gibson said, yeah, we'd like to try that. So we opened our pocketbooks up and we said, okay, try it, right? And out of that came two companies, Panasys and Luster. Luster's not a company, it's technology. And Luster was an open source variant and Panasys was not. And they're both still there today, and Luster is a pretty big thing. And if you don't like Luster, fine, blame it on me. I'm good with that. I was in the room when we funded it. I spent every Thursday afternoon for 4 years with Peter Brahm getting it built. But it's out there serving in the community today. It's doing its job. You may not like how it works. I don't either, but it's doing it. So anyway, these are all good examples of where HPC community and or DOE stepped in. Another one you might recognize there is Ceph. Ceph's a pretty popular thing. So how did Ceph come about? Interesting story. So we had this university investing part of the ASCII program, the Advanced Strategic Computing Initiative program in DOE in late 90s and early 2000s. And it was essentially, there was 3 levels. You could be an ASCII level 1 alliance partner, which was like physics applications. That was $5 million a year for 5 years. Good deal for universities, right? We had a smaller one that was like $500,000 a year for 4 years for technologies, and then we had little ones that were $50K a year, and they were PI to PI kinds of things. And we had lots of this stuff going on. And it was all driven by needs, and we had long lists of needs. And one of those needs was, let's investigate scalable file system security and scalable file system metadata management. Both are hard. They're hard because POSIX rules are how do you do permissions of POSIX, and how do you maintain, you can change a bit in POSIX and it can take away access to a million things all at once. It's cool, but it's hard. It doesn't scale very well. There's all kinds of problems with it. But it's what we had. It's what we had to use at the time. So I went to University of California, Santa Cruz, because they had Darryl Long was there. There were some pretty good people there. And I said, would you do some research on scalable file system security and scalable metadata management? And they said, sounds great. We'll need 3 years at $300,000 a year to build a user space object-oriented file system so that we can research your thing. And then after 3 years, you need to pay us $300,000 a year for 6 more years, and we'll solve your problem for you. And I said, okay, done, go. 3 years later, they had Ceph and Rados and all the things that they had to do. And they hired Sage Weil. Maybe you know him. He's the guy that invented Ceph. Basically authored it at Santa Cruz. And then it turns out that they didn't know how to solve my problem. But they did build Ceph, right? And Ceph is pretty cool. It's a pretty interesting storage system. But it's interesting where it came from. And hopefully some people are getting some good use out of it. We don't really use it in DOE much, but it is an interesting technology. So anyway, there's a bunch of stories like that. Let's talk a little bit about the environment before I get to actual data solutions. So this is our environment circa a few years ago. There's this Trinity system, 20,000 nodes, 2 petabytes of DRAM. It's got this 4 terabyte per second burst buffer flashed here. It's got 100 petabytes at a terabyte a second of spinning disk. And then we have all these capacity machines over to the right, upper right. So think, for capacity machines, for us, think 100,000 cores and down. And then for capability or advanced technology machines, think 100,000 cores and up. That's kind of where the division line is today, and that's changed over the years. So we have lots and lots of capacity machines for running small stuff, 100,000 cores and down, which includes, 2-node jobs and 5-node jobs, all the way up to hundreds of nodes or even small numbers of thousands. There's a site-wide scratch file system for those guys to use. We have a parallel tape archive. We have this campaign disk storage tier, which I'll tell you about in a minute. And interestingly enough, from the data point of view over here to the right, we have this thing called a batch file transfer agent. So that's a cluster, and its job is to move data. That's all its job is. It's the only thing it's there for is to move data. The machines are well apportioned to move the data. You submit a job and you say, I want you to move this 19 petabytes from there over to there. I want you to do it, and I don't want to know. I don't have to restart it. I want you to do it for me. Make sure it happens. And so we do that. So that's what those FTAs are for, is to move the data around. So anyway, that's what our environment looks like. So here's some information about some of the storage systems that we had to build. So this campaign store thing there at the bottom, this is a little vignette about that. So at the campaign store, why did we need that? We needed that because we were going to head towards a world where the first tier of storage was going to be all flash. It was going to finally get cheap enough to be able to have a first tier of storage that was all flash. Nice. It's petabytes of flash, $10 million, but you can do it. and it's going to make users really happy, but it can't be really, really big because it's pretty expensive. So you need a tier of storage below that. And it needs to be fast enough, but not nearly as agile or anything like that. And so we needed a tier of storage below flash and above tape. And of course, that means disk. And disk is high capacity and not very good performance. And then we only needed it to go 100 gigabytes a second or so not super fast in our world. It didn't necessarily need all of POSIX, but it needed some of POSIX because people love that. They like the POSIX file system kind of semantics. It could be immutable. It could, there's all kinds of things it could be. It needed to handle things like keeping data there safe for 2 to 4 years, which is not like the hot tier. The hot tier, the data stays there for weeks or months. If you leave data there for longer than weeks or months, you better damn will be using it a lot or you're wasting a lot of money. So anyway, that's what it had to do. It had to deal with billions of files, billions of directories, and potentially trillions of files, and files all the way from a byte to 100 petabytes. And we're a pretty typical site. All of our data is in the big files, and all of our files are just a nuisance. But and it also needed to have multiple writers into one file. Why? If you try to write 1 petabyte size file and you don't have multiple writers, you'll never finish. So that was the requirements. We looked out there and said, golly, couldn't we buy this? Couldn't Ceph do this, please? We don't want to have to write this software. Somebody, please do this for us, right? Well, we just didn't find anything. Of course, this was going on 8 years ago, so it was a while ago. So we kind of wrote it ourselves, although we took a lot of parts from other places, but we kind of wrote it ourselves. And there's some interesting reasons why we had to do that. But it's interesting what turned out. So we built this thing called Scalable NearPosix thing. So basically it's a namespace sitting on top of an object store. And we were hoping we could at least buy an object store that would fit the bill. That didn't turn out to be true either for different reasons. And so what did we do? We built this thing, and I probably shouldn't take you through the details. Again, it's a POSIX namespace sitting on top of a bunch of objects, and it's deployed this way. There's file transfer agents that send data to it and from it, and there's multiple metadata servers. I mean, it's not rocket science to build one of these things, but what did we find out? We found out that if you put a lot of disks on the floor, and what is a lot? Say 50,000, 100,000, a lot of disks. Not Microsoft or Azure size disks, not that many, but a lot. What happens? Interesting story. So we fund this thing at Carnegie Mellon called the Parallel Data Lab, and it's been there forever. And a student was giving a talk at a retreat. And the student had gotten Backblaze data. Backblaze is a backup site. They provide all their failure data for their disk drives to the world. It's free. You can download it. And it's really neat. You can study it. You can look and see what failure rates look like. You can see failure incidence rates and all that kind of stuff. And the student was doing a really cool project that said, failure rates happen like a bathtub curve. Disks fail a lot when they're new, and then once they work for a while, they're pretty stable, and then when they get old, they fail again. This is very common in failure analysis. And they said, there's money to be made there. You don't have to protect it as much during the middle. You can protect it at the first, and you can protect it at the end, but you can protect it less in the middle. And for people at big scale, okay, I'm big scale, you can save some money by changing your protection scheme during the middle of the life. Great, and wonderful thing. Perfect. The problem was, in that bathtub curve, there were 2 blips. And we said, what are those blips? And they said, we don't know. That was noise in the data. We smoothed it out. So I turned over to a friend of mine who runs Azure and said, you think those are, real? And he said, oh yeah, I know what those are. Because he's bigger than I am by a lot, right? And those are what we call correlated failures. So all the research out there in the world says the incidence rate's random, and it's going to happen based on the bathtub curve. And so you're just going to lose a disk here and a disk there. That's what's going to happen. And occasionally you're going to lose 2 disks there. And occasionally you're going to lose 3 disks there. Well, it turns out there's these other things that are way more sinister than that. And you may lose way more than disk drives than that. Why? What can happen? I called Backblaze and I said, explain these blips. And he said, that one's when one row got really cold. And then a few days later, we lost like 40 drives. Okay, that's a correlated failure. It's not random incidents. It doesn't come in that way. It's something that caused it. So I asked him what the other one was. And he said, that was bad batch from Seagate. And so I'm sitting there thinking, my goodness, there's all these correlated failures. What are we going to do about it? And I myself induced them. Why do I induce them? Well, I probably have hot rows. I'm sure I do. I got tons of rows. I'm sure one of them's hotter than the other. I look a lot like this problem, right? In fact, I use them in correlated ways. I'll spin up 30,000 of them to write a petabyte out. And I'm going to use them exactly the same way for a really long time. I'm my own problem. So how do you fix yourself with that? So we looked and looked to try to figure out what to do about this problem. And of course, the classical way you fix, fix disk failures is you use erasure. Lots of erasure codes out there. You can have some spare, calculate some parity essentially, and have some redundance. All great, except for if you start running the analysis on these things against these correlated failure events, it doesn't hold up very well. And this graph essentially was done by John Bandit DDN, who's now at Seagate. Basically, he did this analysis that said in order to lose 180 disk drives, which is at the bottom, that's that far blue line going up, to lose 80 disk drives, to protect yourself from that, in single tier of erasure, you would have to have 170, have to have 44 plus 16. And how many people you think use 44 plus 16? Nobody. And to get yourself clear down on that bottom line, you'd have to have 170 plus 70. Well, first of all, do you think we can even calculate a plus 70? That's a lot of calculations. The expense to calculate that is crazy. And so we were trying to figure out what to do. What do you do about this? Well, we came up with this idea that you could use one tier of erasure on top of another. So you can take a 10 plus 2 and then take each one of those 12 chunks and do a 17 plus 3 on each one of those, and you get more 9s than you can eat, and it costs you almost nothing. 30% overhead, which is pretty much standard, and you can calculate it trivially because plus 2s and plus 3s are simple to calculate. It became pretty cool. And so this is a perfect example of where LANL gets pushed into these things because of our scale and because of the way we use it. I asked Microsoft, I said, why do you not care about this? And he said, Gary, you're weird. You're the only one that writes a petabyte out there, and if you lose a single byte of that petabyte, you've lost the whole petabyte. We don't have that problem at Microsoft. We've got 700 trillion 1 gigabyte objects or less. If we lose a byte, we lose a gigabyte. When you lose a byte, you lose a petabyte. 6 orders of magnitude difference. And so, sure, we're big in weird ways, so we have to come up with these solutions. But this is a generic fix to a really interesting problem. This is how we did it, 2-tier of erasure. I've explained that already. And we thought about it and we said, you know what? This extends to tape. The same system that does all this erasure could, it's all done using Intel AVX instructions on servers. It's open source code, you can have it. It's Berkeley licensed, so you can even make money off of it. It'll work across tape too. So it's interesting solution. On to the next thing. So how do you move all this data around, in some reasonable amount of time? And a long time ago, we realized we needed tools for this, and we came up with this tool called PFTool, which has been around since I wrote the first version in '93. So it's been around for a long time. It's probably been rewritten a few times. what it is a parallel data mover. So you say move this file or move these millions of files. And what it will do is it will do it all in parallel. It'll load balance it across as many things as you give it. And it will break up the big files into pieces and move them. And it will package the little files into chunks and move them in chunks. And it does statting in parallel, read in parallel, copy, or it'll even do compare between two things in parallel. And it's restartable. Why do you need to restart it? Because it takes a long time to move a petabyte or 10 petabytes or 100 petabytes. So if you can't make it restartable, you haven't even done anything. You'll never get done. So it's a pretty cool utility. It's been out there for a really, really long time. And if you have a lot of data to move or a lot of data to compare or compare the metadata, it's an interesting tool. And it's the kind of thing one has to do in data management in our world, is to have some sort of heavy mover technology. DeltaFS, this is really cool. So we were thinking about our problem of when we do a simulation, let's say we have a petabyte in DRAM, and it represents a bunch of cells in a mesh, and there's a bunch of floating point values in inside of each cell, and you write all this data out. And remember, back in the AMR picture, we only care about a little bit of it. We don't care about all of it. And so any one time step, you only care about the interesting parts. So we started trying to develop technologies to attack this. How would we get retrievals to retrieve only little pieces of what we need and not the whole thing, so that we have to sift through it and find what we need? So we started with a super simple application. It's called VPIC. It's particle in cell. And what does it do? So there's a cell, a grid of cells, and the cells never change. So think a million cells. And then there's a trillion particles. And the particles move around, and they don't stay in the same cell. They're moving around all over the place. And it's representing a plasma or something like that. And so you run this application, and there's physics going on, and it's causing the particles to move around. And every time step, you want to know what cell the particle was in. And so you want to record every time step what cell each particle was in. And at the end of the calculation, the scientists will say, there's 1,000 particles that are interesting. These 1,000 are really cool. I want to know more about them. Where have they been? Show me the particle trace of where they went. And so this is interesting. So the domain scientists said, what we should do is we should write a file per particle per time step. 1 trillion files per time step. Well, that's not going to work. Not too many file systems would do that. But they had the right idea. And so what we did was we wrote a little library that said, you can think you're writing a file, but really you're not. You're writing a record into a key value store, database-like thing, and it's sharded across 1,000 of them. And guess what? The key is particle ID. So that at the end, when they get done writing it all, they give me the 1,000 particle IDs, and I go read 1,000 records times the number of time steps, and a speed up of 1,000. And that's pretty cool. It's super simple, crazy, crazy simple, not really representative of the real workload we want to do, but it was a good proof of concept. And it won best paper at supercomputing and a bunch of other stuff. I think I just described that. And this is the improvement. The graph on the left is, the rule is you can't use much memory on the compute nodes because they're full of application memory. So to do this work, you can't, you can use like maybe 5% or less of the memory. You can't use any cycles on the compute node much at all. So you have to do almost all this stuff offline from the compute node. And you have to do it at basically the same speed as you wrote the data out, just flat. So you've got to add this indexing capability at the same speed that you would have done it if you didn't add the indexing capability. So that was the goal. That's kind of what we did. That's the difference between the baseline and the DeltaFS in time it took to do the dumps. And then on the right, of course, is the 1,000x improvement. And it's scaled out to some number of cores, particles, I mean. And so anyway, it's interesting work. Best paper at supercomputing, best student paper at supercomputing, and really pretty cool work. And so we said, you know what? We should generalize that. We should turn that into a general facility for indexing stuff on the fly from simulations. Sounds like a good idea. It's pretty hard. It sounds like a good idea. And why would we want to do that? We got 8 billion inserts a second the last time. Well, why is it we need more? Well, we don't necessarily need to go faster. We need more function. We need more capability. So we were going after a multi-dimensional index instead of a single-dimensional index. That was a single-dimensional index. It was crazy easy to shard because we were charting on particle ID. Now let's do something real and really hard. Let's take an AMR application that's got from time step to time step, doesn't even have the same number of cells. So how do you even come up with a cell ID? Because the cells are changing all the time. And let's say that the thing you want to do is track the wavefront of one of these eddies or something. Maybe that's the analysis you want to do. How does one do that? How do you contemplate building an index that would go find all that stuff? And of course, the visualization people have done a lot of work in ISO surfaces and R trees and OC trees and all kinds of fun computer science stuff that helps you with some of this. But how do you do it in storage? It's hard. Well, we solved how do you come up with a cell ID or a placement in the mesh ID? You just steal from somebody else. Microsoft did this thing called Farsight, which essentially said, well, just make the key be dots, right? And so you can keep adding dots as long as you start, doing these subdivisions in AMR, and you can describe these things pretty concisely that way. And key value stores can deal with pretty reasonably sized keys, and so this seemed like a pretty good way to do it, and it seems to work pretty well. But really, what are you trying to do? You're trying to track a wavefront in time or something like that, something pretty hard. And what are you going to need to be able to do that? You're going to need multiple dimensions of index, and it's going to be on fields that don't shard well. So we've got to figure out how to do multiple dimensions of index. I'm talking about global ordering across 1 million cores. How do you do that? Well, we think we can figure out how to do global ordering across 1 million cores. If you're writing it out, write it out to 1,000 LSM trees. LSM trees will do local order. And so if you do gross ordering with the cores, bigger than a breadbox, send it over there, smaller than a breadbox, send it over there. And within those, an LSM tree will get, you don't have to write it in order, but you can retrieve it in order. So parallel LSM tree technology, we think, will solve that problem. You have to write, if you want a foreign key, a secondary key, if you want multiple dimensions, you've got to do that twice. So it turns into more of a columnar problem and less of a row problem, which is pretty common. So we think we figured out how to do this. We wrote a library to start investigating this. We're working with technology providers like SK Hynix and Samsung and others to start figuring out whether we can embed some of this stuff into flash controllers themselves. That work is going on and showing some progress. There's actually going to be a demo in the fall. But what turned out to be the hard problem? The hard part of the problem ended up being, how the hell do you shard something that you have no idea what the distribution is? How do you build a fairly even sharding of a bunch of stuff that you have no idea what that distribution looks like? You don't know. If you shard it wrong, you're going to get a hotspot and you're going to go so slow you wish you hadn't done this. You've got to find a way to shard it in such a way that is fairly even. How does one do that? So we started playing with ideas, and the one we came up with that seems to be working relatively well is, if you're doing simulation, classical simulation that's across nodes and across processes, you're sending your surface to your neighbor. You don't send the volume to your neighbor, but you send the surface conditions to your neighbor every time step, so that your neighbor can collect the energy that you emitted to them, or whatever it is you're doing. And so it turns out that the network sees about 15% of your data just doing surface transfers. 15% might get you a pretty good guess at what the distribution is. But if you're an AMR shop and you do an AMR and you're changing where the boundaries are all the time, it turns out the network gets to see more like 30, 35, sometimes as much as 40% of the data over a fairly short period of time, seconds, minutes, something like that. And now you're talking about a pretty good sample of the data that the network has seen. So how could the network help you? It's seen all this data. How's it going to help you? You've got to find a stupid, simple way for a network to help you, because networks are pretty simple, although really they're not. Turns out all you got to do is keep some histograms. You just tell it that field number 4, I'd like you to keep a histogram of all those things you see. And if it can then report back to you when you query it and say, my histogram looks like this, and the other one says my histogram looks like that. And all I've got to do is a collective operation, collect all that information, reduce it into a single, this looks like a pretty good shard based on all these histograms. Make my index like that, write the data like that, and turns out it works fairly well. And it cost almost nothing. We had to move the data anyway. All we did was keep some histograms. Now, sure, I had to pay, Mellanox to give me the ability to do that, right? But the 1000x that I'm going to get at the end of the show, it may be worth it, right? And so that's another super interesting example of interesting data management techniques that are going on that have a lot to do with industry. We have to pay industry to go do these things. We have to do it in such a way that's usable by lots of people. It can't just be for us. But there's a lot of codes that do these sorts of things. I'll talk about Goofy. Goofy is interesting. At Lanol, we have a bunch of these storage tiers, right? I talked about that. There's the hot tier, there's the campaign tier, there's the archive tier, there's home and project space, right, that you mount to get your source code and all that kind of stuff, right? So there's all this space. And we've been around for a while. We've got data in hierarchies that isn't even 8-bit bytes. We have 7-bit byte data. We have 56-bit word data from CDC machines. We can still interpret it all. We know what it is, we know how, but it's been there a long time. So we have old trees. We have lots of new trees because we can create files like the wind, but we have lots of old trees too. So we've got kind of a long history, probably as long as there is in the industry, of trees. So how does one contemplate where you put stuff, and how does one contemplate finding something that you put in that set of trees? And you might say, well, where do you put it? That's easy. Let a policy deal with it. It's been there longer than 4 weeks. It automatically goes from this tier to that tier. That is wonderful for sites that have 1,000 users and 400 codes, and you want to treat everybody sort of equally bad or good, depending on how you look at it. You just set a policy, and that's the policy. Maybe you have 2 policies because you've got some people you really like and some people you don't like, whatever it is, but it's sort of general. We don't do business that way, remember. We don't have 400 codes, and we don't have 1,000 users. At any one time, I've probably got 10 hot users, and that's on a big day. Usually it's 2, and they're eating the whole thing. And so if that person decides to turn left, that policy's going to not turn. And I'm going to probably order a train load of tape. And I don't want a train load of tape, right? And so we think the user, at our site, it's all PI-driven science. It's all PI-driven computational science, and they're doing really big things. And they should make the decisions about where things go. And no, they don't like it, but with a good tool, they accept it. And we needed to provide them with a good tool for how do you deal with managing millions and millions of things that are spread across these, trees that are 40 years old or older, and some of them are 10 minutes old. And so we had to figure out whether there was a way to go do this. And this was a number of years ago as well. There's a couple of products out there that scrape file systems and they make databases out of them. And people can query those databases and they can make decisions usually about policy management. But and system administrators can query that and say, you know, how much data do I have that's really super old, that's never been touched in a long time? I'm going to call a manager and complain or whatever. But we wanted users to be able to access it because we want to push this on the user, because ultimately the user in our site needs to make the decision because the user is so big. We needed a system that you could pull all the metadata out of those file systems and make it available safely with all the POSIX rules, but the user be able to query the queries, as well as the administrator needs to be able to do it too. And if you take POSIX and you try to flatten it into a sharded space or into a big monolithic database, you can't do the permissions anymore. Because remember, POSIX has got this weird, you change a bit way up here and all of a sudden you can't access all this other stuff and all these unlinks and all these things that are hard to do in database land if you flattened it all out. And it turns out there's really not much of a better way to do it than the way POSIX has done it if you're POSIX. In fact, if there's one thing that gets exercised in an operating system, it's traversing the file system. Every command you type, it traverses the file system to figure out whether you're allowed to do that or not. Everything you do is looking up. You can be typing along, and it's trying to figure out what you're doing to finish what you're doing for you. It's just beating the crap out of the file system or the file system metadata all the time. So that code is actually pretty good. Why not use it? So that's what we did. We had this goal. We wanted to provide this thing. We wanted users to be able to access it and get any information in way less than 5 seconds. And any admin to get information about the entirety in some small number of minutes. Well, how does one do that at our size? How big are we? Okay, well, we have about 100 million directories across all this stuff. And we have about 1 billion files across all this stuff. It's not Microsoft size, but it's big. It's distributed, and again, it's old. How does one do that? So what we did was we replicated the tree without the files, with all the permissions. And then we put a database in every directory that had the file information in it, and we set the permissions of that database file equal to the directory permissions. So it turns out that whoever could access that directory can access that database and get that information. And that's cool, and you can do a breadth first query, fire up as many threads as you want, and go down this thing as fast as you want, and do these queries, and put them together and sum them and whatever you want to do. And it's all SQL. It's written with SQLite. So it's tiny, little, fast, cool thing. And it's way faster than the file system. But it didn't get anywhere close to meeting our goal. It wasn't fast enough. Why wasn't it fast enough? Because it's still 100 million opens of a database. And that's still a lot. It's way less than 1 billion stats. But still a lot of opens. So we scratched our head and said, what are we going to do about this? This is hard. And we said, gosh, I wonder how can we get rid of some of those databases? And if we did so, how would we do it? And this is how we did it. We walk to the bottom of the tree, the bottom level. We go up one level and we look below us and we say, is everything below me the same permissions as I am? And if everything below me is the same permissions as I am, I can take all the information that's below me and roll it up to me. And then I move up a level and I do it again. And then I move up a level and I do it again. And I move up a level and I do it again until I get done to clear almost to the top. And what happened was we have this canonical test, 100 million files, 10 million directories. You can represent that with about 10,000 databases and have exactly the same POSIX permissions and let POSIX protect it for you just by doing this roll-up activity. And that sped it up to where it's so lightning fast. Well, actually, we rolled it up too far and we couldn't get enough parallelism, so we had to unroll it again a little bit just to get enough parallelism. And so that's interesting. It's interesting because now, actually, for that canonical test, it's like way less than 1/10 of a second for any user to look up anything. And for the admin, it's less than 5 seconds. And so that works out to work for our billion file problem that we have. It's incredibly fast. It's very secure because it's just using POSIX. And then we took it one step further and we said, okay, why did we do all this? Let's build an index so people could find things. Well, we did it because we wanted them to be able to find things, but really we also wanted to be able to have them annotate those files if they would. This was experiment 94, and it had to do with these things. And in fact, they're even willing to put that in their job scripts so that they annotate them as they make the files. But they're not willing to if there's no way to query it. What's the point? Well, so we've got to figure out how to let them annotate the files and be able to search them in this thing. And it turns out that's possible. And the way you do that is through extended attributes on the files, which POSIX file systems have. And if you put those in the databases, then you can query it at these same speeds. However, there's a catch. And the catch is extended attributes aren't protected the same way that the directories are protected. They're protected the same way as the files themselves are protected. You have to have read access to a file to read its extended attribute. You don't have to have read access to the file to stat the file. You have to have access to the directory. So how do you do that? Well, we did the same thing. Again, we looked and said, how many of the files in this thing, in this directory, don't have the same permissions as the directory itself? And for those, we have to have a separate little database that only that person can access. That added 111 extra databases to the 10,000 that we had to roll it up. Cost zero on the query. And it's simply because of the way UMasks work and the way POSIX permissions work and all the inheritance in POSIX. It just is what it is. So where do we take this? Well, we put it in this tool because it's cool and fast and people may want to use this tool, and we have people using it both at Atlanta and other places. But it has bigger implications. If you can walk out and say that you can represent 10 million directories with 10,000 things, there must be an implication for Linux itself, right? Linux isn't taking that into account. It's doing it the hard way. So I had a discussion with the kernel developer that does this, who we love and hate, and a professor at Wisconsin who does file systems research and award-winning kind of guy. And he had built a file system that was a research file system that was partially in the user space and partly in the kernel space, which is unusual. And what he chose to do is put what's known as the dentry cache, the directory entry cache, in the user space to experiment with these sorts of things. And it was primarily to help Linux grow up and be faster at walking and statting and things like that. And I gave him this information and I said, hey, did you know that if you shard that 10,000 ways, and you can do that with safe permissions, you go like 47 times faster or something. And so it may make its way to the kernel someday, we think. It's pretty enlightening. We didn't anticipate that. We didn't know that's where we would land, but that's where we landed. Let's see, what else do I have? I've talked about all that. On to students. Atlanta students pipeline is very, very long and very, very robust. As you can see, 71% of all technical people are hired from our student programs. We have 1,900 students a year, which is the largest student program within any DOE lab by quite a bit. Goes all the way from PhD, from postdocs all the way down to high school students. although we don't have that many high school students. In my organization alone, HPC, we have 60 a year. In the computation and statistical sciences division, they have about 90. In computation total, I would say it's easily 700 or 800. And so there's a ton of opportunity for internships at LAL, more than any other national lab. And even in the business side of the laboratory, there's internships. And we have this institute, another outreach, essentially building clusters and putting applications on them, which was replicated by supercomputing itself, which is kind of cool. And that's it. That's all I prepared. Hopefully it was interesting.
Thank you, Gary.